Today I'm going to talk about our recent work on the mechanism of aggregation-induced emission. So we know that in nature, many molecules have this phenomenon called aggregation cost quenching, that is ACQ. So for these molecules, in their dilute solutions, they emit light strongly, but in their solid or concentrated solution, the fluorescence just gone. Okay. And these molecules typically have a planar and rigid structure. And the reason for ACQ is in general attributed to the electronic coupling between two adjacent molecules. Okay. And we know that in nature, some molecules behave oppositely. So in dilute solutions, they don't emit light at all, but in concentrated solution or solid, their fluorescence is very intense. And this phenomenon is called aggregation-induced emission, or in other words, AIE. Okay. And typically for AIE molecules, their structures are not planar. Okay. They have lots of bulky groups, and this bulky group can rotate along the CC single bonds. And this phenomenon now is almost becoming a household name in the Chinese research community due to the systematic work by Professor Pen Zhongtan in the last 20 years. Okay. And for such an abnormal and very interesting phenomenon, there are many mechanisms proposed to explain this phenomenon. And among them, this one is the most popular. And it is stated in the chemical review paper published in 2015. Okay, so this is their central idea, the red marked, the sentence marked by red. The friction caused by their rotational or twisting motions against each other with the solvent media transform the photonic energy into thermal energy. Okay. This mechanism is that energy gets conserved. So the electronic energy must be equal to the rotational energy or vibration energy or both. So molecular motions in liquids produce frictions to dissipate electronic energy. So this explanation sounds reasonable, but let's think about a fundamental question. Where does the driving force for the CC single bond rotation in room temperature liquids? Without electronic excitation, can the carbon atoms rotate around the single bond? Let's think about the nature of transition state theory. Okay. Now, if you want to understand the exact mechanism, let's go back to the detail about excited electrons. We know that when electron goes to the excited state, eventually it gets to go back to the ground state, right? And the energy difference between these two states will be released in terms of either visible photons and or vibrations, rotations, and translations. If the radiation decay is faster than the non-radiation decay, then the quantum yield of fluorescence is larger than 50%. And the radiation decay rate constant can be estimated with the spontaneous emission equations. And then you will plug all these normal organic molecular parameters into this equation. We got the emission time constant around 10 nanoseconds, which is consistent with the fluorescence lifetime, a few nanoseconds to tens of nanoseconds for most organic molecules. Then how can I estimate for the non-radiative decay rate? At this, we can use the direct energy transfer.
11 to 11:30 time.
Yeah. And then we can use the diffusion energy transfer equation we developed in the past 10 years, okay? And also when we plot the molecular parameters into it, we found that the non-radiative dissipation rate is around 5 nanoseconds, which is similar to the radiated time constant, but slightly faster. And this actually the estimation results are consistent with the fluorescence measurement. We know that many organic molecules, their fluorescence quantum yield is around 10% to 90%, and typically it's more than 50%, which indicates that the non-radiative decay rate should be at the same order of radiation decay, but slightly faster. Okay. Then we certainly know some molecules has fluorescence quantum yield smaller than 0.1%, meaning the non-radiated time constant should be around 10 picosecond or faster. And such a non-radiative decay is too fast for the direct electron vibrational energy transfer within the wave coupling limit. So this dissipation must occur within the strong coupling limit. And for this case, theoreticians already create a name for it called crossing canonical intersection. Okay. Then what does canonical intersection mean? Okay, for many people, they just, it's a very strange name. Okay, now let's look at this picture. We know that the photon emitted, its energy should be equal to the energy difference between the electronic excited state and ground state. But if the two states have the same energy, so even if the electronic transition occurs, but this transition will not emit photons, is that right? Certainly it's right. But is this scenario possible? I know to many people, or to the intuition of many organic chemists, it's just simply impossible. But in fact, this is quite universal, okay, in nature. As early as 1937, okay, Taylor already wrote a paper to describe this phenomenon very carefully. Okay. So for example, as shown in this figure, a molecule may have an electronic ground state and excited state, and for each state, it has different potential surfaces. Okay, and at certain conformations, its excited state energy may be the same as the ground state energy, and at this point, those two states are degenerate, and this point is called canonical intersection. And the reason why it's called canonical intersection because the two potential surfaces intersect on one point. So the shape actually is exactly like in a canonical, right? Canonical point. And mathematically, it can be very easy to be described. As you can see from this equation, if the two states are degenerate, then the denominator is 0. Only if the numerator is not 0, then the coupling between the two states can be very big, right? So which indicate that any linear combination of the electronic excited state and ground states should be the solution of the Schrödinger equation. Or in other words, on this conformation or on the canonical intersection point, the molecule has two identities, electronic ground state and electronic excited state, and each has 50% possibility. Here I want to use two animations to show you the physical picture of canonical intersection. Okay. So for example, I have one molecule, it has two nuclei and one electron. So if the electron absorbs a photon and be excited to it, to the electronic excited state, so the electron certainly goes far away, and then the two nuclei are separated. Right? So for the same molecule, instead of excited by a photon to the electron, the chemical bond absorb vibrational energy and they are separated. And because these two nuclei are separated away, and then certainly the electron get to jump away. And so for the molecule is at the electronic ground state, but it is at the vibrational excited state. Now we compare these two different cases. For the final state, they're exactly identical. Now, if we look at the final structure, then certainly we don't know which pathway it is from, right? It comes from, okay? And then because of this, for this particular conformation or this particular final state, we call it is a canonical intersection, okay? Because it may come from two different pathways. One pathway is because of electronic excitation, while the other pathway is because it is from the vibrational excitation. And then at this canonical intersection point, the electronic excited state and vibrational excited state, the vibrational excited state of the electronic ground state, they are under fast equilibrium. They can convert into each other within tens of femtoseconds. And for electronic excited state, they dissipate energy very slowly at around 10 nanosecond time scale, okay, as we just discussed. For the Wake-Coupling limit and for the spontaneous emission. However, for the vibrational excited state of the electronic ground state, it dissipates energy at a much faster time scale, around 1,000 times faster picosecond time scale. Okay? And then you may ask me why these two mechanisms have so different kinetics. Let's look at another animation. For example, this is electronic ground state. And then the red one is the electronic excited state. If the molecule is at the vibrational ground state, the electronic excited state, when it releases energy, so this molecule get to go directly from this excited state, go back to the ground state. So it get to release, all the energy with, let's say, within one step, and release a photon of large energy. And because in the environment, there are no resonant acceptors for this energy transition. So this process gets to occur by the slow spontaneous emission pathway or the very slow non-resonant energy transfer to the vibrational modes. However, if this molecule is at the vibrational excited state of the ground state, so when it releases energy to the environment or when it relaxes, it does not release energy within one step. Instead, it releases energy step by step from one excited state to another excited state. And the energy gap between two vibrational excited states is only a few thousand or 100 with numbers. And in the environment, there are so many resonant acceptors, so that the resonant energy transfer is much faster than the non-resonant transfer. Because of this, vibrational relaxation typically much faster than the spontaneous emission. Okay. Now let's go back to the AIE phenomenon. We know for many AIE molecules in their solid, their fluorescence quantum yield is larger than 20%. But in their solution, the fluorescence quantum yield may be only 0.1%. So which means that in the solution of these AIE molecules, the non-radiated decay time constant is around 10 picosecond. Then according to the discussion, this must be caused by canonical intersection crossing, right? Then we're good. So this explanation seems to be very reasonable, intuitive. Why wasn't mentioned in the review? And certainly we don't know, we are not the authors. But we can ask a further question. So if this explanation is right, then did anybody mention it before? In order to answer this question, let's go back to check the history of AIE. So as early as 1896, the AIE phenomena was already mentioned in a paper, certainly written in German. And then in 1913, Stark already did very systematic research on this phenomenon. And between 1960 to 2000, actually many nice pieces of work were done to try to rebuild the mechanism of AIE. And most of the research concluded that the mechanism of this AIE molecule probably similar to that of ethylene. That is, probably this that functional group must rotate around the CC double bond, and by rotating this double bond, they must cross a canonical intersection. And then for the most related research is this paper published in CanCom in 2013 by Professor Blankenford in Spain. So his research group did ab initio calculations on a AIE molecule, and their calculations suggested that this molecule has a canonical intersection to release its electronic excitation energy in solution. But very unlucky, this molecular system does not have any observables that can be experimentally directly tested. And 3 years later, a group led by Professor Kommenbaugh at Switzerland ran ND simulations on another AIE molecule, TPE, and their calculations suggested this molecule may have two possible pathways to cross different canonical sections in dilute solution. So one pathway is similar to ethylene. So the 4 benzene ring can rotate around the CC double bond to have these so-called 6-chance isomerizations. But they found that this pathway is only the major, play a major role for the energy dissipation for this molecule. The minor role, but the major role is the cyclorization between 2 adjacent benzene rings. Okay. Now, certainly, as we know that in MD simulation, it's very difficult to precisely catch the structural evolution around this canonical intersection point. But anyhow, this paper is informatic. So 2000 later, Professor Van Dontan's group did some ultra-fast visible pump experiments on TP solution, but certainly probably because of technical difficulty, they could not perform measurements on TP solid. So they did not come with very solid conclusion from that experimental results. And then I think that what we really need is to follow the structural evolution after electronic excitation. In order to do it, we get to monitor the vibrational frequency and cross-angle evolution after electronic excitation. For this purpose, so we build a ultrafast UV IR mixed spectroscopy. Okay. And then it was built by 2 of my grad students, Jianxin Guang and Jie Peng. So these are the spectrum. These are the spectra from their setup. And my colleague, Professor Zhao, at PKU, synthesized all necessary molecules for our studies. Now let's look at this very classical AIE molecule, TPE. Okay, it has very similar FTIR spectra for solid sample and dilute solution, okay, as we can see here. And then after excitation, it's solid. The TPE solid behave actually quite similar as the FTIR spectrum, right? The 2 peaks. Okay. But for its dilute solution, after electronic excitation, the infrared response is very different from the solid sample. Right? A new peak grows in at a different frequency than the two frequency in FTIR. And we know that in general, there are two possible reasons for the growth of new peaks in this type of ultra-fast infrared measurement. The first one is the direct constant change induced by excitation, or the second one is the formation of new structure. We know that for the first reason, the signal must occur instantaneously. Well, for the second possibility, it will take some time, okay, for the new structure to grow. Now let's look at the data. For the solid sample, the signal reaches maximum at time 0, but for the solution, the signal reaches maximum at 10 picoseconds. So, which means that, okay, for the solid sample, the signal must mainly from electron vibrational coupling. Well, for the solution, it is probably comes from new structure. Then what would be the new structure for this new peak? And then according to organic chemistry, the most likely structure would be this cyclization product. Okay. But according to calculations, this cyclization product is very unstable. It's around 2 electron volt less stable than the most stable conformation at the ground state. Then how can we experimentally verify the structure of this cyclization product? Then of course, the most direct evidence is the vibrational frequencies. As you can see that according to our initial calculations, the cyclization product has exactly the same frequency as what we measured. And then certainly you know that one frequency is not sufficient to identify the molecular structure. And actually we measure all vibrational frequency that we can measure and turn out to be the experimental results fit the calculation very well. And so in order to further verify our result, we use a different technique, mass spectrometry, to further confirm this conclusion. As we can see from this pump-hole measurement, we know that the cyclization product lifetime is very short, only around 200 picoseconds. However, if we can oxidize this cyclization product, it can form a very stable molecule on the right. And then we can use mass spectrometry to directly test the existence of this cyclization product. In fact, for all the AE molecules we measured, they all, after electron excitation, they all form this cyclization. And the cyclization product, can be detected after oxidized. And also, according to our spectral analysis, we found that in the dilute solution, more than 70% of these TPE molecules forms this cyclization product. Okay. And then now this comes to the central question. Why doesn't the molecule emit light once the cyclization is formed? Now let's look at the potential surface of this molecule, then we'll immediately understand. Because once the molecule is excited to the electronic excited state, then it must go through a canonical intersection before it can cyclize, right? It can form this cyclization product. Or in other words, once we see the cyclization product, which means that this molecule already goes through a canonical intersection. And at the canonical intersection, this molecule releases most of its, actually releases all its electronic energy into vibration. And then we can, okay, then why it doesn't form this cyclization in the solids? Actually, this is kind of easy to answer, because we know that in order to reach the canonical intersection, the benzene rings get to twist, to rotate. But in the liquid, this kind of easy to do, right? Because the barrier is small. But in the solid, the rotation get to break the crystalline structure. The energy barrier is too high. Then it's too high. However, even in the solid, the molecule cannot go through a canonical intersection, which only means that it does not dissipate electronic energy very quickly, right? But this cannot guarantee the molecule does not go through the aggregation cause quenching effect. Then what are the possible factors that can make these AIE molecules have very high fluorescence quantum yield? I think this we can also easily explain, because we know that for this TP molecule, it has 4 side group benzene rings, and all these 4 benzene rings are not coplanar. So in the solid, these 4 benzene rings are very bulky, okay, and then they can make the center chromophore are well separated from each other, and because of this arrangement, the 2 adjacent TP molecules in the solid are only weakly coupled, and which effectively prevents the aggregation in cause quenching effect. Then certainly you may ask me, how can you test this proposed mechanism that the side group actually has the effect of separate 2 chromophores further away? Okay. And experimentally, it's actually quite easy. It can be tested with anisotropy measurement. Okay. As we know, in the solid, 2 adjacent molecules have different orientations. So once the energy are charge transfer from one molecule to the other, the anisotropy of the signal, electron excitation by Bragg detection, must change. Okay, must change. And if the change is larger, indicate the energy of charge transfer is faster, which certainly is caused by stronger electronic coupling, right? So let's look at the result. For AE molecules, within 20 picoseconds, we don't see any anisotropy value change. However, for ACQ molecule, we can see very clear anisotropy value decay or grow within a few picoseconds or tens of picoseconds. So the result tell us that for these major AIE molecules, the anisotropy change is very slow, indicating a very slow energy of charge transfer. Well, in the ACQ molecules, the anisotropy value change much faster, so indicate a faster energy of charge transfer. Certainly stronger electronic coupling, so stronger quenching effect on these ACQ molecules. And then this conclusion can be further verified by the crystalline structures. As you can see, for the TP molecules in its solid, the separation between 2 molecules is around 8.6 angstrom, or in the ACQ molecule, the distance only 4.9 angstrom. So if we just only consider this distance difference, it already causes around 24 times difference in energy transfer rate. So at this point, I think we can come to the conclusion. That is, the mechanism of AIE includes 2 parts. Okay. The first one is that in the dilute solutions, the electronic excite state get to cross a canonical intersection point to fast release electronic energy, so that its fluorescence is extremely weak. Well, in the solid, the molecule cannot cross such a canonical intersection because of the environment constraint. Okay, and in addition, the bulky side groups two adjacent molecules are well separated, okay, so that the molecule in the solid can fluoresce intensely. Okay, and these two factors combine together to make the AIE phenomenon occur. Then certainly, we come to this conclusion just based on the measurement of a few molecules. So we got to ask, is this conclusion general? And further, can we learn from this study to create new ways to control emission efficiency? And as we just, from this conclusion, we know that the nature of AIE of these TPE molecules essentially is that in the solution, the molecule has a relatively low barrier to reach CI in liquids, while the barrier in its solid is much higher. Okay. So certainly they come with the first idea. Do we have other ways to tune the barrier to reach the CI? And further, can we control the appearance of CI to control the emission efficiency? So before we go further, let's look at a very famous rule in photophysics, the so-called Vebleo's rule. So this rule states that the emission efficiency is independent of excitation wavelengths. And then certainly we know that this rule is not suitable for molecules with multiple chromophores or multiple excited states. But even for, let's say, single excited state, does it still hold? Now let's look at the very basic fundamental assumption for this rule. We know that for a molecule, if this molecule is excited to the electronic excited state, no matter which vibrational state it is excited to, it always relaxes back very fast into the vibrational ground state, and then slowly dissipate its energy by emitting photons within nanosecond time scales. Okay. So even we use different wavelengths to excite this molecule, the light of different wavelengths only excite this molecule to different vibrational excited states of the electronic excited state, right? So no matter which vibrational state it is excited to, it always goes very fast to the vibration ground state, and then emit light slowly by the spontaneous emission process. And because of this, the fluorescence or emission quantum efficiencies is independent of the excitation wavelengths. So this is actually the origin of molecular principle of Vebleo's rule. But now, because we know that for these AA molecules, it has very special potential surface. So its electronic excited state may have a canonical intersection with the electronic ground state. So let's look at this, the potential surface. So if this molecule is excited by a longer wavelength, then certainly this molecule goes to a lower vibrational ground state, right? So it has the energy barrier to cross to reach the CI, let's say delta E1. If it is excited by a photon with a smaller wavelength, now this molecule goes to a higher vibrational excited state, right? So the energy barrier for it to cross to reach CI, delta E2 actually is smaller, right? It's smaller. Okay. Or in other words, if the wavelength is longer, then its barrier to cross to reach CI actually is larger. So which means that it is slower to reach CI, which means that it is slower to non-radiatively release energy. So if the non-radiated decay is slower, then the emission quantum efficiency should be larger, right? So from this analysis, we immediately understand that if the molecule, AIE molecules, have the mechanism we just proposed, then these molecules must have different fluorescence quantum yield dependent on the excitation wavelength. If the excitation wavelength is longer, then the quantum efficiency must be larger. Now let's look at this, molecule, trans-stilbene. Okay, it is also an AIE molecule. So when it is excited with 260 nanometer light, its fluorescence quantum yield is only 2.9%. But when excited with a longer wavelength, for example, 320 nanometer, its emission efficiency is 4.2%, around 50% higher. Exactly similar to what we just predict based on the AIE mechanism. Okay. And also because of this, because of this mechanism, accidentally we just were able to tune not only the emission efficiency, but also the emission wavelengths for a molecule by the amplitude of more than 200 and very close to 300 nanometer. Actually, by tuning this molecule, either cross or not cross a CI. Okay, so let me stop my talk here, and then I want to thank my colleagues and my students, and also the funding agencies to make this work possible. And thank you for your attention.